specific heat capacity means nothing but like the quantity of heat required to warm a given substance. Okay, required to warm a given substance. Yeah. So it depends on mass, change in temperature, nature of the substance. If the nature of the substance changes, I can say that like the specific heat capacity also changes. Okay, so heat capacity like amount of heat that must be added. Okay, added in the sense what happens here? Added from the object in order to achieve a small change in its temperature. Okay, so S is equals to delta Q by M into delta T. So what is S here? S is nothing but the specific heat capacity, and Q is the heat, M is the mass, and delta T is nothing but temperature. Okay, so when we talk about the SI unit, it is joules per Kelvin inverse. Okay, so delta Q amount of heat supplied to the substance, and delta T is the change in temperature from T to delta T plus 20 plus delta T, like that small change in temperature. Okay, take a note of this. Done? Can we go for the next topic? Completed? Okay. So when we talk about the specific heat of water, ice or steam, okay. So what is the thing like we are talking water, ice or steam? Solid, liquid and gas. Solid in the sense ice, liquid, water and gas is steam. So for different cases, different values are there. Okay, so a value of specific heat of water is nothing but around 4200 joules per kg degree Celsius. Okay, so the value is 4180, but for the calculation purpose we take around 4200. And when we talk about specific heat of height, it is nothing but around 2100 joules per kg degree Celsius, and specific heat of steam is nothing but 0.46 calories per gram degree Celsius. So I have given the conversions also. Joules per kg degree Celsius, calories per kg degree Celsius, kilocalories per kg degree Celsius, and calories per gram degree Celsius. Okay, and this is the three values, different values for solid, liquid and gas, that is ice, water and steam. Okay, so here is the question, a simple question. Heat required to increase the temperature. Increase the temperature. Heat in the sense delta Q I need to find, right? Temperature of 1 kg of water, meaning mass is 1 kg and water, we know that what is the water? 4200. Okay, 4200, that is joules per kg degree Celsius. So if the question is mentioned in terms of this SI unit or this SI unit or this SI unit or this SI unit, I need to take accordingly. Okay, here they have taken like 20 degrees Celsius. If they are asking in the joules per kg degree Celsius, we need to use this one. If they are asking calories per kg degree Celsius, we need to use 1000. If they are asking kilocalories per kg degree Celsius, 1. So similarly calories per gram degree Celsius also 1. So easily we can say that conversions, right? So calories to joules, right? No, 1 calorie equals to 4.2 joules, right? 4.2 joules. delta q one side and the remaining values the other side. So delta q is equal to m as delta theta. So 1 into 20 is nothing but 20. Yes, 20 kilocalories. Okay. So 1 kg of water, 1. And this one, the value of S, we will take it as how much? Kilocalories, no? 1 kilocalorie there as 1. And the value of change in temperature is 20. So 20 kilocalories. Okay. So S is equals to 1 calories per gram degree Celsius. And 1 kilocalorie is nothing but 1 kilocalories per kg degree Celsius. This is gram and this is kg. Okay. Take a note of this. Done? Done. Can we go for the next one? So next point, like when a substance changes its states, okay, changes its states is in what is the meaning of that? So from liquid, solid to liquid, liquid to gas, solid to solid in the sense the stage is not changing, right? Yes, no? Yeah. Solid to solid, the state is not changing, but solid to liquid, the state is changing. So formula is nothing but S is equals to Q by M into delta T. But the thing we need to observe here, when a substance melts or boils, its temperature does not change. That is, delta T will be equal to 0. But it still absorbs heat. Q is not equal to 0. Remember the points, okay? When the states are changing, delta T is not equal to 0. Q is not, delta T is equal to 0. Q is not equal to 0. So S is equal to Q by delta T. Right now, S is equal to delta Q by M into delta T. When this is 0 in the sense, something by 0 is nothing but infinite. Means infinite specifically. So example, ice melting at 0 degrees Celsius or water boiling at 100 degrees Celsius. So temperature constant but heat still observed. Okay. So this is one of the important point. You can take a note of this. So they might ask a question based on this. Okay. Like a theory part. heat must be removed. So Q is negative. I'm removing something. Removing something in the sense when you're getting negative. Okay. So adding something in the sense positive. Okay. So specific heat is negative. Okay. I'm removing something. No. So S is equals to minus Q. It will come. No. So minus Q by something. So the total value become minus. Okay. So yeah. Heat capacity or thermal capacity. Okay. Heat capacity or thermal capacity. It's the amount of heat needed to raise the temperature of a body by 1 degree Celsius. Okay, so which means heat capacity is equals to M into S. Okay, so what is CGS unit? Calories per degree Celsius, and SI unit is joules per Kelvin. Okay, so relation between specific heat and water equivalent. Okay, so they might ask question on this water equivalent. So water equivalent means how much water would be absorbed the same heat for same temperature change as the object. So since water is value is 1, no, we are talking about specific heat, right? No, equivalent like S is equals to 1. Then what is the meaning of that? Ms delta T is equals to Ms delta T. Like this is for water, mass of water, specific heat of water, and changing temperature. Okay, so S delta T will get cancelled. Okay, no, only delta T and delta T will get cancelled off. Okay, and Ms, so this and this will be equal. Okay, here we are talking about water equivalent, that is nothing but W is equals to Ms. Okay, so Ms is equals to mass of water. Okay, so the next one, law of mixture. Okay, law of mixture is nothing but when two things. Okay, mixture is nothing but mixing something, no? So when two substances at a different temperature, so when I'm taking hot water, I'm taking cold water, if I mix together, what it becomes a normal water. But if I take a cold water, it becomes cold. I mean, it's a cold only, right? No. If I take a hot water, hot only. But if I take hot and cold, it will become a normal because of the temperature, right? No. So two substances at a different temperature mixed, heat flow from hotter to colder one. It's not going from cold to hot. Hot to cold it will come, right? Now, if I take a hot cup of water, tea, anything, if I keep in a room temperature, what happens? Because of the surrounding, it becomes cool, right? No. So similarly, this transfer of heat continues until both reaches the same temperature. Yes, no. When I keep something in the surrounding, it becomes the surrounding temperature only, right? So the final common temperature is called as the mixture of temperature, thermal mixture we will say, and the formula is M1S1 T1 minus Tm is equals to M2S2 Tm minus T2. What is Tm? The mixture temperature. T1 is the hot temperature and cold temperature. Okay, so I can write this as Th minus Tm will be equals to here. It is Tm minus Tc. Hot mixture, cold mixture, cold. Okay. And yes, if you see here, M1 is nothing but mass of hot substance, S1 is nothing but specific heat of hot substance, and T1 is nothing but initial temperature of hot substance, and M2 mass of cold substance, S2 specific heat of cold substance, and T2 is nothing but initial temperature of cold substance. Tm is final mixture temperature. So most of the cases they will ask this to find, okay, to find the mixture, temperature of mixture. You can take a note of this. It's an important point. thermal equilibrium. Okay, that's why we are taking the equal condition equation. Okay, so yeah, we'll talk about a problem. So here is the problem. A sphere of 0.047 kg aluminum is placed for sufficient time in a vessel containing a boiling water, so that the sphere is at 100 degrees Celsius. Okay. It is then immediately transferred to 0.14 kg copper calorimeter containing 0.25 kg water at 20 degrees Celsius. The temperature of water rises and attains the steady state 23 degrees Celsius. Calculate the specific capacity of aluminum. Listen carefully. Okay, listen carefully. They have given the mass of an aluminum sphere 0.047 kg. Initial temperature of that how much? 100 degrees Celsius. Okay. And what happening here? It rises and attains steady condition. Steady state, no. Steady in the sense after mixing together, then it becomes a normal condition. Okay. Final temperature is 23 degrees Celsius. So changing temperature how much? 100 minus 23, which is nothing but 77. Okay. So let's specific capacity of aluminum we'll take as it is. Okay, we'll take as it is. Amount of heat loss. Heat loss is the Q we are calculating. So M1 S1 delta T. So what is M1? 0.047 and this one I don't know, and this is 77. So I can equate now. So aluminum and copper both I can equate it now. Yes. So now what I am doing here, what we are doing here, mass of a water 0.25 kg, mass of a calorimeter 0.14 kg. So initial temperature of water in calorimeter is 20 degrees Celsius, and what about the final temperature? 23 they are given. So what is the remaining? 3 degrees Celsius. There it is 77. Now specific heat of water, we know that 42 100 4.2 into 10 power 3 we can take, right? Yes, no? And specific heat capacity of copper calorimeter they have given. Now I can add both of them now. When I why I am calculating like this? We are taking the water and inserting that calorimeter because both is same, right now. So M2SW plus M3SCU. What is water? And this is copper into delta P2. Okay. So we'll get some values over here and we'll equate both of them. So when we equating, see, heat lost by the aluminum sphere equals heat gained by the water and the gained calorimeters. Okay. Done. So we'll get the answer as 0.91. Okay. Okay, I guess it's clear right now. I guess the voice is coming right. Hello. Yes, the Eagle 78939 voice is coming right. Okay. Okay, then we'll go for the next one. So change of state. Change of state in the sense we are transferring. I mean we are changing the solid to liquid, liquid to gas. Right now, solid to solid in the sense there is no state change. Right now, state change in the sense nothing but going from Telangana to Andhra, Andhra to Tamil Nadu. Not like that. It's from solid to liquid, liquid to gas, like that. Okay. So transition from one state to another is called as change of state. Okay. And solid to liquid, liquid to gas. So when we talk about the solid to liquid melting, And when we talk about liquid to gas, it's a boiling, right now. So I'm taking ice. If I start melting the ice, it becomes a water. If I start again heating that, it will become a gas, right? No, so changing the state. Okay, so please try to adjust my diagrams. Okay, so melting, the change of state from solid to liquid. So melting point is nothing but the temperature at which solid and liquid state of the substance is in thermal equilibrium. Okay, thermal equilibrium in the sense like solid is there, like some amount of solid. I am taking ice, completed water, but some condition will be there. No, both will be at thermal equilibrium. Okay, that's the thing we are talking, melting point. So vaporization means change of state from liquid to a vapor. Okay, or gas we will talk. Okay, so boiling point is nothing but the temperature at which the vapor state, liquid and the vapor state are in thermal equilibrium. Boiling point, one more is melting point. So sublimation is nothing but change of state from solid to gas directly without coming to liquid. Okay, solid to gas directly. Okay, example dry ice. Example dry ice. When we talk about dry ice, no. So if I take in hand, it becomes vapor easily. Yes, no, dry ice. So it doesn't melt, right? No. Yeah. So relegations. The phenomena of freezing is called freezing, refreezing. Okay, refreezing. Okay, so take a slab of ice and take a metallic wire and fix two blocks. Okay, so okay, no need about this part. Like we need the meaning of the relegations. Okay, refreezing. Excuse me. Okay, now the latent heat. It's one of the important topic here. Okay, heat is added to given the quantity of ice at minus 10 degrees Celsius. Okay, here. Okay, so minus 10 degrees Celsius. No, like minus temperature of ice increases up to 0 degrees Celsius. At 0 degrees Celsius, what happens? The addition of more heat does not increase the temperature but causes the ice to melt. Ice to melt. It doesn't change anything, but it starts melting. Okay, adding more heat will cause this temperature of water to rise up to 100 degrees Celsius. Okay, 100 degrees Celsius. Again, what happens if I increase at this point? It becomes gas. It becomes gas. At 100 degrees Celsius, the amount of more heat does not increase the temperature but causes the water to vapor. Okay, water to vapor. So it is the amount of heat. Latent is nothing but it is amount of heat transferred during the change of state of substance. That is nothing but Q is directly proportional to M. To remove the proportionality, we are adding constant called L, latent heat. So if mass is there, heat also there. If more mass, more heat. Okay, so L is equals to Q by M. When we are talking this latent heat, when the solid thing is there, no changes to liquid. So in this case, what happens? State has been changed. So initially minus 10 degree to 0 degree Celsius, right now. So it is ice only. So I should use specific heat capacity. That Q is equals to ms delta T, right now. But when 0 to, like it's changing the temperature, no, and changing the temperature in the sense changing the state only. In that case, I should use Q is equals to Lm or ml. Okay, so I should add the thing. We'll see the problematic point of view. Okay, so here latent heat of fusion is nothing but solid to liquid. So value is 3.3 into 10 power 5, and latent heat of vaporization is nothing but liquid to gas, which is nothing but 22.6 into 10 power 5, 3.3, 22.6. Okay, so take your values. What we are doing? Taking water is there, okay? We are mixing the ice, okay, in a container. The resulting temperature is 6.7 degrees Celsius. Calculate the heat of fusion of ice. Calculate the heat of fusion of ice. So if S is equal to 4186, you can take 4186 or 4200 also approximately. Okay, so you have a solid 1 minute time to give the answer for this question. We'll see. Okay. See, heat lost by water, no? Right now, heat lost by water, and then what we are doing? Heat required to melt. Right? No, both things we are doing. Heat lost by water in the sense mass of water, specific heat of water, changing temperature of the water. Right now, 0.3 into 4200, like 41 to 86. They have taken 4200 also. You can take, and the temperature is 50 minus 6.7. Right? No, 50 and 6.7. So we will get around 54,000. Okay. Heat required to melt. Heat required to melt in the sense M into L. So 0.15 into L. Okay. Now when we talk about these two things, we can equate the things, right? So when we equate it, what happens here? So this is heat required to raise the temperature of ice water to final temperature. So mass of ice, specific heat of water, and the temperature. Okay, what we are doing first? 50 to 6.7, 6.7 to 0. Right now. So we are getting 42. So 4206. Now heat lost equal to heat gain. Heat lost equal to heat gain. I have told the things no. Q is equals to ms delta T and Q is equals to ml. I can add the things. Q is equals to ms delta T plus m into L. When we are using this, when the states are changing. Okay, when the states are changing. So this one m into L and this one ms delta T, and we are equating and we are getting as 3.3 into the power 5. Okay, this is the thing we have got. Yes, no, latent heat of fusion. Right? You can take a note of this. So on the previous slide. will